Thanks so much for having me today. I'm going to be talking today about a technology called eBPF, which I have been fascinated with for the last few years, really. And I'm going to talk about how it gives us superpowers with the tools that we can use in DevOps environments, whether we're talking about observing our applications, making sure things are running correctly, whether we're talking about connecting our applications together with networking tools, whether we're talking about security. eBPF gives us this incredibly powerful platform. Now, I have just written a book called Learning eBPF, which is really designed to help people understand eBPF concepts by getting into the code level. And that might not be appropriate for lots of people here. You may not particularly want to get into the coding of eBPF. But one of the things I wanted to highlight was a quote that Daniel, who's one of the two co-creators of eBPF in the Linux kernel, Daniel had pointed out as his quote for my book that eBPF started a whole new infrastructure movement in the cloud native space. And that kind of power of the platform is really what I want to talk about today. So the acronym eBPF stands for Extended Berkeley Packet Filter, but you can put that out of your mind because it does so much more than packet filtering now. What eBPF allows us to do is run custom programs inside the kernel. Now, if I'm going to talk about the kernel, I should make sure we're all on the same page about what I mean. So usually our applications run in user space, but whenever they need to do anything particularly, or anything that touches hardware, whether that's reading or writing to a file, sending or receiving network messages, even if you want to allocate memory, then your user space code can't do that by itself. It has to ask for assistance from the kernel. And it does that using a system call interface that we usually don't care about. If we're writing programs, the programming language we use typically gives us abstractions that are sort of way above that system call interface. So we don't normally need to worry about that. But the fact that all of our applications, whenever they do anything interesting, are invoking the kernel is really key to the power of eBPF. Because with eBPF, we can attach our custom programs to events that are happening in the kernel. Those events could be a system call being made. It could be any trace point or any function call within the kernel itself. It could be trace points or functions in your user space code. It could be the arrival of a network packet into the system. There are lots and lots of different events that we can attach our eBPF programs to, and we can use that to either observe the event or perhaps even influence what happens as a consequence of that event. So a really basic hello world example would look something like this, where in this example, it's just going to trace out the words I'm alive, and we could attach it to a system call called execve. I'm not going to show this one live for now. I've got another live example I'll show you later on. Every time any new program gets run on the machine where this program is running, that's going to invoke this system call, execve, and that would result in the line of trace being generated. So every time a new executable was run, we'd see a line of trace. And we'd get some information about the context in which that program was executed. So it's one of the really important things about eBPF programs is they can gather contextual information about that event that triggered them. And that can be really powerful in terms of the observability information that we can collect. So we can dynamically change the way that the kernel behaves. And that's really a game changer in terms of how quickly we can modify the code that runs in the kernel. So when you're running your Linux distribution in production, maybe it's something like Ubuntu or Red Hat or Debian or whatever the distribution is, it's going to be using a version of the Linux kernel that was probably released 2, 3, 4, maybe even 5 years ago. So the distributions make choices about how recent a kernel they want to use. So if you want to make a change to the Linux kernel, not only do you have to get the whole community, including Linus Torvalds, to accept your change, it's going to take years before that upstream kernel actually arrives in a production environment, unless you're going to use a very cutting edge kernel. With eBPF, we can write programs, load them dynamically, and it can change the behavior of the kernel straight away. You don't even have to reboot your machine, and you can affect the way the kernel's running. You might be thinking, well, couldn't I write a kernel module? Isn't that another way to customize the kernel? And it's true that you could, but kernel modules are typically considered quite dangerous, because if there's a bug in a kernel module, it could crash and bring down your whole machine. And that's a bad day in the office. The difference between writing a kernel module and running an eBPF program is what's called the eBPF verifier. As you load an eBPF program into the kernel, it goes through a verification process that analyzes the program and makes sure that it's going to be safe to run. It checks that it cannot crash. It examines every possible path through the program. It ensures that it's going to run to completion, so it can't lock up your machine. The verifier is really fundamental to why eBPF code is safe to run. So I'll give you an example of a situation where it's really useful to be able to update your kernel dynamically. And that's a situation called the packet of death vulnerability. This would be a bug, essentially, in the kernel where a particularly crafted packet, well, the kernel doesn't know how to handle that packet properly and crashes. There have been a couple of instances of these packet of death scenarios in the past. So malicious attacker can send a carefully crafted packet and deliberately bring down your machine if this vulnerability exists. Now, the traditional way to deal with this would be to apply a kernel patch. That's going to involve applying that patch and rebooting every one of the machines in your deployment. With eBPF, we can write a program to look at that packet and dynamically discard it. I'm going to show a really quick example where I'm going to pretend that ping is malicious. So let me start by, I'm going to make sure we can write out tracing from the kernel. And I'm going to start by running ping. And you'll see that every second that ping is sending a request, getting a response, and we can see the sequence numbers just continuing to tick up, and that will just carry on for a while. And I'm going to run a network program, an eBPF program here attached to my network interface, and I'm going to drop the packet. If it's a ping request, don't worry too much about the code, but if it's a ping request, I'm going to drop the packet. So let's got a little script that's going to run that program, and we should immediately start seeing the pings will stop, but we'll see tracing on the right hand side. And there we go. So we can see the packets are being received and they're being dropped, and the sequence numbers on the left hand side have stopped ticking up. I could modify my program to say, you know what, just trace out the fact that the packet has been received, but well, I'll just delete this bit. So this is going to trace out the fact that it's a ping packet, but it's going to let it carry on as before. And let's apply that. And what we start seeing now is packets aren't being dropped anymore. They're still being seen by our eBPF program, and the pings have started again. Now, the point of that example is to demonstrate that I could apply those eBPF programs dynamically and immediately change the behavior. And I didn't have to reboot the machine. I didn't have to do anything to reconfigure networking. I just ran my eBPF program and attached it to the network interface. And it was able to examine and, in that case, discard packets. So I hope that gives some illustration of the power of eBPF programs. Now let's have a little consideration of what this means in a Kubernetes environment. So I talked about how user space code uses the kernel whenever it wants to do anything with hardware. When we run our applications under Kubernetes, those applications are inside containers, inside pods. But all of those pods, all of those containers on a given machine or virtual machine are using the services of just one kernel. There is only one kernel per host machine. So whenever our application code is doing anything interesting, that kernel is involved. The kernel's also involved in coordinating between multiple different processes that run on that machine. So if you do things like create containers, or if Kubernetes is creating containers and pods, again, the kernel is involved in that. So the kernel is aware of everything that's happening across that entire host. If we instrument that kernel with eBPF, we can be aware of and we can affect what's happening on all of our pods without having to change those pods at all. So that is the basis for a whole new generation of observability tools, networking tools, and security tools that we can use in cloud native. So I want to do a little tour around the cloud native landscape and show a few tools of these different types and the kind of powerful things they can do. Let's start with observability, a project called Inspector Gadget, which was recently added into the CNCF sandbox. And the reason I wanted to mention this is it's a great example of using eBPF in conjunction with Kubernetes and getting this Kubernetes awareness. So there's information here about the Kubernetes pod, the container in that pod, the node it was running on, as well as in this example, it's showing, it's tracing out when a file's being opened. And so we can see not just that a file has been opened, but exactly which container in which pod has done that. And Inspector Gadget has lots of different types of tracing, types of observability that it can show you at the command line to see what's happening in your Kubernetes cluster. Another example of observability would be networking observability from the Cilium project. Hubble is the observability component inside Cilium, and it can show you individual packets, a little bit like we could see the tracing just now showing us each individual packet that eBPF was observing. We can see individual packets flowing through a Kubernetes network. It's got that Kubernetes identity awareness, so it can show us how those network flows map between services. We can build up a picture of how different services are communicating. And it's also hooked into Prometheus metrics. So you can see all manner of different interesting metrics about how networking is behaving and observe those through really nice Grafana integrations, Grafana dashboards. Another observability tool in the cloud native landscape is Pixie. So a little bit like Inspector Gadget, this has a whole range of different eBPF programs that you can use underneath it. Pixie will allow you to deploy those and gather the information from across your entire cluster. So this is an example of a flame graph showing CPU usage aggregated across an entire Kubernetes cluster, which is pretty cool. So let's move on from observability to actually tools that affect the way the system is behaving. And I'm going to start with networking. So you've seen already an example of eBPF manipulating network packets. This is really useful for efficient networking in a cloud-native world. So traditionally, container networking or Kubernetes networking, our pods they run in a separate network namespace, and that means they have a separate networking stack. And that networking stack is connected to the host's networking stack through a virtual Ethernet connection. A packet that's coming from the outside world to the application running in that pod has to pass through the host's networking stack and then cross over that virtual Ethernet connection, go through the pod's networking stack to reach the application. With eBPF, we can essentially intercept that packet as soon as it arrives. And because Cilium is aware of the Kubernetes identities and how those relate to the IP addresses for where this packet is destined, Cilium can use eBPF to intercept that packet and redirect it directly into the pod's networking namespace. The shorter the path that the packet has to take, the lower the latency, the faster that packet can be processed. And this achieves real results. Not just Cilium, but other implementations of eBPF as well are demonstrably significantly faster. So in this example, we can see that if there was no container networking at all, that's the blue line on the left, the eBPF implementations from both Cilium and Calico, this is taken from a couple of years ago, so it's probably even better now, but they're almost as fast as if there were no container networking at all. Whereas the host routing versions, where the packet has to pass through the whole host networking stack as well, are significantly lower performance. We can also accelerate service mesh in a similar way by shortcutting the path that network packets have to take. In service mesh, we typically have a sidecar approach where there's a proxy injected into every single pod. And as you can see on the left-hand side, that makes a pretty convoluted path for every network packet. In a sidecarless model that we can implement in Cilium using eBPF, we can often bypass and shorten a lot of that network path, and that leads to high performance. And some other benefits because we don't have to inject sidecars. Let's consider that a little bit more. You've seen that we can inject eBPF programs into the kernel and they can affect applications without having to make any change to the application or anything else that's running on that machine. A couple of years ago, Nathan Leclerc did this really nice little cartoon, which I think illustrates how eBPF is a more modern approach to instrumenting our applications than the sidecar model. So in the sidecar model, we inject our tooling into our application pods as a container. So you maybe have a tracing tool, a logging tool, and if you want all of your applications to behave in a consistent way, you'd inject that same logging and tracing container into every single application pod so they can do the same kind of tracing as each other, or they can do the same kind of logging as each other. Now, by design, pods are isolated from each other. So if you want a sidecar to have visibility over the pod, it has to be inside that pod's namespaces. And that means it can only see what's happening inside that pod. If you want to share configuration information, for example, you need a different copy of that configuration information for every single sidecar. This is particularly relevant in service mesh, where you might have routing tables. And you need a copy of the routing table in every single pod. With eBPF, because our programs are running in the kernel, we only need one instance, and we only need one instance of the configuration information. Even if we're configuring that in user space, we can share that information between a user agent and the eBPF programs in the kernel using a concept called eBPF maps, which allow us to share data between kernel and user space. The other problem with the sidecar model is that you have to configure sidecars. They don't get into pods by magic. They get into pods by YAML configuration. Something has to create that YAML. It's usually automated. Maybe it's a webhook or the CI/CD process that adds your sidecar containers into each pod. But if we're using eBPF, we don't have to change that YAML at all. So there's no possibility that misconfiguration can mean that some of your pods end up not instrumented. If you instrument the kernel, all of your pods are automatically visible to those eBPF tools. And not necessarily just your pods that you've legitimately deployed. If an attacker somehow compromises your cluster and runs a workload, runs some kind of malicious activity in that cluster, that is also visible to your eBPF tools. Whether that's going to be observability, you can see the fact that the process is running, or even some kind of preventative security tool. So that leads us on to the next generation of security tools that are being built with eBPF. Now, one security tool that is kind of obvious to folks who are configuring networking, but doesn't necessarily you don't necessarily think of it as a security tool, but it's network policy. So Kubernetes has network policy built in, but it has to be implemented by your networking plugin. And using in an eBPF networking implementation like Cilium, it's dropping packets exactly like we saw in the demo, just inspecting packets. If they don't meet the network policy, then it can drop them, just like you saw me demonstrate. Here I'm showing the network policy editor, which is a really great tool if you want to build or verify that your network policies are behaving the way you expect them to. So check that out at networkpolicy.io. Another security tool that you may have come across that has an eBPF mode is Falco. So again, this is a CNCF project, and you can see here an example of a rule, very much like the Hello World example I showed you right at the beginning. This looks at programs that are being executed using that execve system call, and that's detected using eBPF. When it finds that a new program is being executed, a user space tool evaluates whether, in this case, it's a malicious or very likely malicious program called Netcat, which you probably want to know about. So this is giving you insights into security relevant information. Cilium has a new subproject, or relatively new subproject, called Tetragon, which does a similar kind of approach, but it's actually filtering the policy events within the kernel. So that's even more efficient. And again, using that Kubernetes awareness to show security relevant information. In this example, access to files inside the etc. directory. Tetragon also has the ability to enforce policies, so it can actually prevent, or it can kill a process that's attempting to do an out of policy action. So I think I've shown you a range of different tools there from the cloud native landscape that are very powerful eBPF based tools. you do not need to write eBPF code yourself to take advantage of eBPF as a platform. Typically, people are going to use tools that have been built that are, complex tools in much the same way that you don't write your own container runtime engine. But if you don't want to write code yourself, but you want to dive more into the technology and what it enables, I wrote a short report called What is eBPF? If you are interested in diving into the code and getting a feel for how it works by kind of going under the covers a bit more, then let me recommend my Learning eBPF book. Either way, you can try out lots of eBPF activities at Isovalence Labs, and you can also download both of those books and also a security observability book written by some of my colleagues. You can get all of those for the mere cost of your contact details from the Isovalent website. So with that, I hope I'm just about in time. I'm going to try and move back to camera. And there we go. I realized I was going to run a poll at the beginning to ask whether people were already familiar with eBPF, but
we did,
the excitement
actually.
of getting the technology to work, I forgot all about it.
Yes, the poll was actually, by the way, starting with thank you, Liz, so much. And about your question about the poll, we did run the poll here. And now we see the results as well.
Wonderful.
Just a second, Mark is looking
Fantastic.
for it.
Yes, so the first eBPF, I don't know anything about it, 82.9%. So.
Okay.
Yes.
Well, hopefully, if we ran the poll again, we would get a slightly higher number who think they do know a little bit now. They've seen some examples.
True.
Yep, and 16% have seen some talks. And thank you once again, Liz. It's absolutely amazing to have you here. There was a bunch of Q&A. We have quite a few things for you.
Yes. This question coming from the chat, would you say that this is actually the biggest kernel innovation that we have right now?
Almost ever.
Ever,
right?
Yes.
Yeah, without wanting to, minimize all the other amazing things that have been done in the kernel, I do think this is a real game changer because it crosses the whole way that the kernel can behave. It gives us this programmability that we've never seen before. So, yeah, I think there's a good argument to say this is one of the most revolutionary changes that's ever been introduced into the kernel. I might be biased because I think it's just fascinating.
I do too. I'll highlight, there was lots of people want to know more, and I think everybody at almost any level that is doing any type of technical work should know about eBPF. Do you agree, Liz?
I think it's really good idea to have an idea of the concepts behind it. As I say, I don't think everybody is going to end up writing their own eBPF
Absolutely.
code because it's kernel programming, and most of us don't write kernel code either. We have plenty to do writing application code, or operating applications. But I think having a sense of what eBPF can do for you and how eBPF tooling, the kind of things that it can enable, and also, having a good understanding of, eBPF, with great power comes great responsibility. You want to be very confident that you're not loading malicious eBPF tools. Having an understanding of the power of it, I think, is really important. Yeah,
absolutely. So there's been a lot of talk, and you covered some of this in the speech, and I've also heard you cover it in some other forums. But there was a question like, is eBPF a kind of kernel module? And then you've got like your sysadmins who are familiar with kernel modules, but they're not as familiar with eBPF, and they don't really understand the security concerns or the differences between those. Could you open that up a little bit for our audience, please?
Yeah. So, as I mentioned in the talk, if you're running a kernel module, you obviously hope and believe that it's well tested, but there is the possibility that there's a bug in that kernel module, and if it results in a crash, it brings down your whole machine. The risk of that is, I think, it puts people off quite a lot from using a kernel module approach. I know a lot of organizations will be very hesitant about using kernel modules. The fact that you can dynamically load an eBPF program so quickly and easily, and that that it cannot crash the kernel, it's going through this very rigorous analysis to ensure that it is going to behave in a safe way. I think that gives a lot more reassurance that eBPF programs are going to be safe to run and aren't going to bring down your machine in the middle of the night.
Okay. There's another one that came in that's really interesting. Can someone use eBPF as an attack?
Yeah, really great question. So yeah, with the ability to influence anything and observe anything in the system, you can use that for good and you can use that for evil. That's for sure. And there are certainly things like eBPF rootkits. The real, the thing that people need to take away is, don't install an eBPF program that you don't know where it came from. You are giving that program access and insight, or potentially access and insight, to your entire machine. You have to treat that like root privileges. You have to be very, cautious about the eBPF, the provenance of your eBPF programs. There's actually some work going on in the kernel community around signing eBPF programs. So a bit like the whole supply chain security work that's going on. It's actually really complicated to sign eBPF programs for some really interesting reasons that we could talk about for about half an hour. But it is quite complicated, but there's work going on to be able to give that kind of proof that this eBPF program you're running is definitely the one you expected it to be. Yeah. You can also use eBPF to observe other eBPF programs. It's very meta.
There's actually just now a question from Stavros on the chat right now. Is eBPF mainly going to benefit containerized applications? What would you say, Liz, on this?
Not necessarily. So, a container is just a process. So there's, you can use eBPF to, observe and connect and do all sorts of things with non-containerized processes as well. And in fact, with Cilium, we have lots of users who are connecting their Kubernetes clusters potentially with legacy workloads that are not containerized. And there's actually some really interesting developments going on there to kind of bring that eBPF connectivity right into the VM where those legacy workloads are running. Legacy is a bit of a, non-containerized workloads, let's say.
Okay.
Great, thank you.
Very cool. We'll take a couple more because we're still a little bit early. If that's okay, Liz. So installing and enabling eBPF on a machine.
Yes, you need a kernel that's built with BPF capabilities, and there are some config flags to enable BPF. I think all the major distributions now have that kind of turned on by default now. There's also a thing called unprivileged BPF, which is one of those things that I think everybody in the community would look back and go, yeah, maybe that wasn't such a good idea, because why would you want to give unprivileged users the ability to run these root-like powerful programs in your kernel? That is enabled on some distributions, and that may well be a good idea to make sure that you don't have unprivileged BPF enabled in your machines. Cool. I hope that answers the question.
All right. And Kiran Salunke had a question. Hope I pronounced your name well. on use cases. And this is a question that I asked you before, Liz, but could we explore a little bit some use cases? Because one of the things that I'm kind of interested in and that I see with some of our customers is we're able to get secure access in places that used to have a tremendous amount of bureaucracy. In order for a developer to be able to start something new, for example, or to execute a template from Backstage or something like this. So could you open up a little bit about like some maybe higher level use cases that would affect more of our audience of developers and DevOps engineers and software people?
Yeah, it's hard to know where to start. I think. I certainly tend to think of eBPF as giving us these observability insights, particularly where, well, what are the questions that you want to ask? Do you you might be debugging issues within your platform, or you might be, checking on things like how a resource is being used. I know people have been using eBPF-based tooling for things like some resource usage. There's actually a really great, really interesting project called Kepler that's using eBPF to essentially measure energy usage. So you can see which of your applications are burning the most energy and therefore least green, least sustainable. So there's I think it really depends on, what is your focus? What's the question that you want to ask of your platform? And then often eBPF could be a really good way of getting the data that enables you to answer that question, to get the answers to those questions.
Okay, cool. I want to leave a little bit for Andy and your fireside chat, which if you would like more on this topic, there will be a fireside chat with our dear colleague Andy Allred and Liz later on in the program. Today, yes. Absolutely. So thank you once again, Liz.
Awesome.
It's absolutely awesome to have you with us.
Absolutely, my pleasure. And thank you to everyone who asked questions. I love questions, so that was really great that lots of people had things to ask.
Great.
Okay, thank you.
Bye, Liz. Hi, we're from Ethico, the proud organizer of the DevOps conference.
Our goal is to uncover cutting-edge talks, emerging ideas, and DevOps trends, providing a global forum for practitioners and decision-makers to learn and grow.
We would love to also explore how we can help you excel in DevOps together. Visit us at ethico.com and enjoy the inspiring talks at the DevOps conference.